In this video, we'll discuss how to quantify and compute the reliability of a component or a system of components. Equipment often fails, and the more components there are in a system, the more opportunity there is for one of those components to fail. We'll define the mean failure rate, mu, as the reciprocal of the mean time between failures, and we'll assume that this can be measured for a particular component. If we know that components are going to fail, it's helpful to know how frequently they are going to fail. That is, what mu is, or the rate of failure. The reliability, R, is a function of time that describes the probability that a component will not fail over an interval from 0 to t. Then the reliability, R, at small values of time is usually quite high. That is, the probability of not failure is close to 1. Eventually, a component will likely fail. So the reliability for larger t gets smaller and approaches 0 as t goes to infinity. This is described by an exponential decay, where the decay rate is the reciprocal of the mean time between failures. That is, the rate is mu. If R, the reliability, is the probability of a component not failing in the interval from 0 to t, then P, the probability of failure, is 1 minus R. If there are n components in series, then the reliability of the system is the product of the reliabilities of all of the individual components. The reliability of the system describes the probability that none of the components will fail over the time interval from 0 to t. If just one component fails for a system in which components are in series, the entire system fails. Since reliability numbers are always between 0 and 1, as we take their product, the reliability gets smaller. That is, the more components you have in series, the less reliable the entire process is. However, reliability can be improved by redundancy. The reliability for n components in parallel is 1 minus the product of 1 minus r. In order for a redundant system to fail, all of the components have to fail, because each redundant element can perform the same function as the other elements that it is in parallel with. Let's take a look again at our liquid storage tank with the safety instrumented system consisting of a level switch and a solenoid that can shut off our pump. We'll calculate the annual reliability on this safety instrumented system, assuming that the level switch has a failure rate of 0.4 per year. That is, the mean time between failures is 2.5 years. For the solenoid, because it doesn't get actuated very often, it's very reliable. The mean time between failures is 100 years. So its rate of failure, mu, is 0.01 per year. These components are in series in this safety instrumented system. So we can find the reliability of this system by taking the product of the reliabilities of each of the components. And the reliabilities are computed by the exponential e to the minus mu t. Since we're interested in the annual reliability, which is the probability that the system will not fail in 1 year, t is 1. When we take the product of exponentials, remember, we sum the exponents. So we can compute this reliability as e to the minus 0.41, which is 0.66. So there is a 66% chance that the interlock will not fail in a year. That means that the probability of failure, P, is 34%. That is, there's a 34% chance that this system will fail in a year. That's not a very great reliability. So we probably want to try to improve the reliability in some way. We'll consider 3 alternatives. One is to add a low-level alarm in parallel with the interlock, or the SIS. that low-level alarm has a mean time between failures of 5 years. So its annual failure rate is the reciprocal of 5, or 0.2. A second alternative is to add a redundant level switch that can also activate the solenoid, so that we'll have two level switches in parallel, and that parallel pair of switches will be in series with the solenoid. A third alternative will be to, instead of adding a parallel level switch, add a parallel solenoid. Why would we do that? Because solenoids are cheap and reliable. So we can easily add one in parallel, where the level switch will activate both solenoids, and as long as one of the two solenoids is working, the pump will be shut down. We'll first consider case 1, which is the low-level alarm. If we add a low-level alarm, indicated in green here, then the reliability of the new process is the reliability of our original process in parallel with the low-level alarm. Remember, the reliability of our original safety instrumented system was 0.66. So we can multiply that by 1 minus the reliability of our low-level alarm and subtract the product from 1 to obtain the reliability of these two components in parallel. The reliability of the new system is now 0.94, or 94%. This doesn't mean that the probability that any of these components won't fail within a year is 94%. What it means is that there's a 94% chance that both the interlock and the alarm will not fail at the same time within a year. So if the interlock quits working, the alarm will still alert an operator that the level in the storage tank is too low. That's one of the wonderful advantages of having redundancy. Next, let's consider our second alternative, which is to have a redundant low-level switch in parallel with our original low-level switch, where either of these two switches can actuate the solenoid. We'll assume that the reliability of the second low-level switch is the same as the reliability of the first low-level switch. So the reliability of these two components in parallel is 1 minus R squared. Those are in series with the solenoid, so we multiply that by the reliability of the solenoid. We find that the reliability of this newly designed system is 0.88. So there is an 88% chance that the interlock will not fail in a year. Now, what do you think will happen if instead of adding a redundant low-level switch, we add a redundant solenoid? After all, the solenoid is very reliable. To compute the reliability of this system, where instead of having two level switches in parallel, we now have two solenoids in parallel that both rely on the same level switch, we need to first calculate the reliability of the two solenoids in parallel, which is 1 minus the reliability of the solenoid squared, and then multiply that by the reliability of the low-level switch. We find out that the reliability of this new system is now 0.67. Remember, the reliability of our original system was only 0.66. Adding an alarm in parallel with the entire interlock increases it to 0.94. That's a substantial improvement. Adding only a redundant switch also results in a pretty substantial improvement. Remember that the switch is the component that is more likely to fail. So if we make that component redundant, we substantially improve the reliability. However, adding an additional solenoid does not improve the reliability much at all, and that's because the original solenoid was unlikely to fail in the first place. Adding redundancy of an element that isn't likely to fail does not improve the reliability of the process. Chemical and biological manufacturing processes often involve hazardous materials and conditions that may pose a threat to employees at the manufacturing facility and to people outside the manufacturing facility who happen to be nearby. Process design and process control design are important parts of improving process safety. There are multiple layers of protection that are implemented within process safety. These include the process design, can be done so as to minimize hazards, the basic process control system, which helps to ensure that continuous processes are operating within their design conditions, alarms that alert operating personnel when process conditions are outside the design conditions, safety instrumented and emergency shutdown systems, which are designed to take over the shutdown or sometimes the startup of components of a process to prevent hazardous situations or to prevent damage to equipment. Physical protections such as dikes, drainage, fencing, flares. Plant emergency response, which are personnel trained to respond to emergencies on site at the manufacturing facility. And community emergency response. We talked about the design of different types of alarms and how they are appropriate for different types of situations. We also talked about alarm management. Good alarm management can help us to avoid nuisance alarms and enable operators to better respond to the most important alarms. Finally, we introduced a quantitative measure of reliability and described ways to compute the reliability for systems that contain components in parallel and components in series. Calculating the reliability can help us to choose among alternative designs for control components and alarm systems.